Section 8.2, the reciprocal function family. Yesterday, again, we talked about inverse variation that had the general form y equals k over x. The reciprocal function family is going to have the form y equals a over x plus h plus k. Actually, it's x minus h. X minus h plus k. Transformation rules, things we've looked at multiple times in the past. Not to imply that you all remember them perfectly, but there should be a certain level of familiarity with these. So today should be okay. Shouldn't be too bad. And if we had forgotten the rules for transformations, this I took out of the textbook that some of you guys don't realize exists. Put it here. These are the rules. So we have a stretch and a shrink. If A is negative, it is a reflection across the x-axis. If H is positive, then it's going to, or the H determines how it's moving right and left. The K is determining how it moves up and down. All of these rules should be familiar. Don't ask why having a turd in your pocket would cause you to grin. It just does. Now, we want to graph y equals 128 over x, where x cannot equal 0. So we're going to pause there. What's happening if x is 0? We call it a vertical asymptote. If you plug in 0 there, it is undefined. So graphically what we call that is a vertical asymptote. And we draw our vertical asymptotes as dashed lines. This graph, if we remember from yesterday, the inverse variation graphs, they are also going to have a horizontal asymptote right here at 0. So for your basic run-of-the-mill inverse variation graphs, where you have no horizontal or vertical translations, h and k are both 0, your asymptotes are going to be the x and the y axes, which we saw yesterday. And then the graph is going to be in the first quadrant and the third quadrant. So that's where we paused, is right here. X can't be 0, so we have our vertical asymptote here. And then from yesterday, we saw the horizontal asymptote will be right there. What are the x and y intercepts? So we have that our vertical asymptote is x equals 0. Our horizontal asymptote is y equals 0. So since our asymptotes are the axes, we're never going to touch them. So what are the x and the y intercepts? There are none. Okay? Now, vertical asymptotes you never, ever, ever touch. And in a graph like this, you're never going to touch the horizontal asymptote either. But in the future, you could come across examples where you do cross the horizontal asymptote, but we'll talk about that later. So we have identified the x and y intercepts. There are none. We have identified the asymptotes. It's the x and the y axes. State the domain and the range of the function. The domain for this function, we'll just say x cannot be 0. That's it. It could be absolutely anything else. Just can't be 0. Because if you plug in 0, it's undefined. What about the range? Y cannot be 0. The only value y cannot take on is 0. You could make it anything else. But if it's defined as 128 divided by x, that will never be 0. You could make that as large as possible. If I plug in an x value of 0.000000001, then the value of y is going to be huge, right? 128 divided by 0.000000001, really big number. Or I could plug in an x value of 1 billion. 128 divided by 1 billion, that's going to be a really small number. So I can make y anything really big, anything really small, and anything in between. And then all of that same logic, just with a negative sign, means it could take on all those values and their opposites. The only thing it cannot be is 0. So we need to plot a few exact points. Let's make a table. We know that we'll have the point 1, 128. We know we'll have the point 64, 2. We know we'll have the point 128, 1. Right? And then we'll also have these same exact points just with negative signs. Negative 1, negative 128, negative 64, negative 2, negative 128, negative 1. Let's say each box is going to be worth 10. That's probably going to be the best way to graph this one. Since it is 128, there's not really a great way to graph it without having a huge graph, but let's go by tens. So 1, 128. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's going to be way up there. So let's just put it right. And then we're going to have 64, 2. 1, 2, 3, 4, 5, 6. We're going to be like right there. Right? So this graph is going to be something like that. Right there.
I didn't know that.
From yesterday, we know that that's the general shape. The only thing we didn't write down that there are no intercepts.
And that's just a given.
That's because the asymptotes of the axes, there are going to be no intercepts, x or y. So this is just asking us to reference those transformation rules that I provided in the notes a few pages ago and explain. It's not asking you to graph. It's asking you to explain. How is negative 1.5 over x different than 1 over x? There are different numbers. That's true. That's an incredibly superficial difference. So we know that our family is given by a over x minus h plus k. H and k are not factoring into this problem at all, are they? There's no difference here to here, and there's no difference from something being added out on the outside. So h and k are not providing the difference. The difference is the value of a. Right? In this one, what is the value of a? It's 1. In this one, what is the value of a? It's negative 1.5. So that's all we say. We say this is a stretch by a factor of 1.5. Stretch by a factor of 1.5, and it is also a reflection over the x-axis. That is how they are different. Over the. Although the 1812 overture is the best one ever. So you should listen to it. What is the graph of y equals 1 over x minus 2 plus 3, identifying the domain and range? Let's begin with domain and range. Domain and range. Domain and range are important in functions like this because they are going to tell us where our asymptotes are. Because the domain and range for functions like this are going to be x cannot be this specific value, y cannot be this specific value, and those specific values are going to be your vertical and horizontal asymptotes. So in this case, let's begin with domain. You know that the denominator cannot be 0. That is the basic idea. And you need to think like that for the rest of the chapter, because that's going to be an incredibly important idea for the rest of this chapter, that the denominator cannot be 0. In this problem, the denominator, right here, x minus 2. So we know x minus 2 cannot be 0, meaning x cannot be what? 2. So my domain, x cannot be 2. For range, the idea with range is that the fraction 1 over x minus 2, that will not be 0, ever. It is impossible to make that fraction 0. You can get really, really close, but you cannot get all the way to 0. So close that it's almost indistinguishable, but only almost, right? 0.000000000000001 is really close to 0, right? But it's not equal to 0. So 1 over x minus 2 cannot equal 0, which means that y will not equal 0 plus 3. All I did there is I replaced this with 0 and said that y will not be equal to that. So what is my range? Y will not be equal to 3. So my asymptotes in the graph, which I want to mark as dashed lines, x will not be 2. And so for the scale of this one, we'll just say each box is 1. Make it easy. So that vertical asymptote, x is 2. And then my horizontal asymptote will be at 3. And we have to remember that I'm drawing those as dashed lines because they are not part of the graph, but they will help us shape the graph. So the domain and range, it cannot be those values, but those values are important to the graph. From there, we just want to plot some points and see what's going on. What is this going to look like from there? If I plug in 3, what do I get? If I plug in 3, I get out 4. If I plug in 4, I get 3.5, so that's going to go right here. What if I plug in 2.5? 2.5 gives me 5. Right there. And at that point, with those 3, and our knowledge of what these graphs are supposed to look like, that's enough to show us this. The nice part then is we should realize that these points are going to get reflected down here. And we can always check that. If I plug in 1, what do I get? 2. Right there. If I plug in 1.5, what do I get? 1. What if I plug in 1/2? 5. Right there. So then again, our knowledge of the basic way these graphs look allows us to finish the graph off like that. I've given you the graph. I've told you it's a translation of the graph of y equals 1 over x, and I'm asking you for the equation. Looking at the graph, can you identify the asymptotes? Because that would be really important to know. Try and identify the asymptotes. So we look here, and it certainly appears that the vertical asymptote is right here, x equals -1, and that the horizontal asymptote is right here at y equals 2. Why is that really helpful? We now know that the domain is going to be x can't be -1. We know that the range is that y cannot be 2. I didn't ask for domain and range, so you don't need to write that down, but it could be helpful to understand that. Remembering that the general form for this is going to be y equals 1 over x minus h plus k. Right? Because they told us it's a translation, meaning we shouldn't have to worry about what the a is. A translation just means you took the graph and you slide it either left and right, up and down, or some combination of both. So when they use the word translation, you shouldn't have to worry about this number changing. We're only worried about h and k.
1 over x plus h plus 2.
Right, so 1 over x minus negative 1 plus 2, which simplifies to 1 over x plus 1 plus 2. Reason being, if you remember the first one we graphed, the 128 over x, the asymptotes there were the x and the y axes. X equals 0, y equals 0. And so if you have a graph like this where you know that the a is just whatever, you're not looking for a different a, it stays as a 1, then all you have to do is realize from the origin we went left 1 and up 2. Left 1, up 2. That's it. You just have to remember how the h and the k affect things. And then you have to remember that the general form is x minus h, and so when you plug in that left 1, it's negative 1, x minus negative 1 is x plus 1. That's probably the transformation, the translation that people get hung up on the most. The vertical one is easy. In the end, up 2 means plus 2. For horizontal, hopefully we remember the fact that in the end, left 2 means plus 1. So we have a word problem. Yes, that's a lot of words. Luckily, for most everyone in here, English is the first language. Right? They are asking us to write an equation that models the cost per person. Then it's asking us to use that to determine how many members have to attend for the cost to be less than $25 per person. The model. It's cost per person, right? So the cost per person, that's what capital C represents, is going to be the total cost, which they tell us. The total cost is $6.50. And to get the cost per person, you divide by the number of people paying. They tell us to use n, so how many people are paying? N. Minus 1. Why minus 1? The person that is attending as the dead body is not paying, so the number of people paying is the number of people attending minus the dude playing the dead body. Or, that's sexist, could be a lady playing the dead body. Okay, whoever's playing the dead body does not pay. So this is the cost per person. We have to use that to determine how many members must attend for the cost to be less than $25 per person. So we want the cost per person. All right, we're finished with the first part. We want the cost per person to be less than 25. So we want 650 over n minus 1 to be less than 25. Multiply each side by n minus 1. We get 650 is less than 25 times n minus 1. Divide each side by 25, and we get what? So we get 26 has to be less than n minus 1. Add 1 to both sides. 27 has to be less than n. So how many people must attend? So how many people must attend? We must have 28 less than or equal to n less than or equal to 30. Now I went from 27 to 28 because this says I have to be greater than 27, So I just said greater than or equal to 28. Why am I allowed to ignore all the little decimal points in between 27 and 28? You can't have a fraction of a person. Exactly. So you could have 28 or more. Where does the less than or equal to 30 come from? Because he wants no more than 30 people in the house. So you have to have 28, 29, or 30 people if you want the cost to be less than $25. Now this is an example, guys, of a word problem that I would classify as very difficult, even though if you look at what we did there, none of that math is very difficult. Figuring out cost per person, pretty straightforward. Probably the toughest part there is remembering that the dead body doesn't count. And then once you set this up, pretty easy to figure out from there. Again, at the end, you just have to remember in the problem, they tell you no more than 30. I would classify this as a difficult word problem because they tell you that the group has 75 members, and that does not play any role in the problem. And there are those of you in here that have the overwhelming desire to use every single number they give you. So, we're starting to see these word problems where you have to look through the information provided, and there's going to be some of it that doesn't matter, and you have to be able to recognize that.